All right, let's talk about the biggest monsters in the entire cosmos, supermassive black holes. I mean, these things are absolute behemoths, millions, sometimes billions of times the mass of our own sun. They're the gravitational anchors for pretty much every big galaxy out there. But they give astronomers one massive headache.
How in the world do you study something that is, by its very nature, invisible? You can't. A black hole is a one-way street for everything, including light. So if no light can escape, how can we possibly figure out what's going on at the very edge of reality?
And look, this isn't some far-off, abstract concept. These monsters are right in our cosmic backyard. Most galaxies have one, including our very own Milky Way. Ours is called Sagittarius A star. So, if we want to understand how galaxies work, we have to understand these giants they're built around.
So if we can't see the black hole itself, what's plan B? Well, the answer isn't to look at the black hole, but to look at what it's eating. We study its glowing dinner, and that brings us to the physics of what we call accretion.
Here's the secret. You stop trying to see the invisible thing, and instead, you watch the stuff falling into it. As gas, dust, even entire stars get a little too close, that immense gravity grabs them and pulls them into a swirl. We call this the accretion flow. And this is where things get really, really bright. Think of it like water going down a drain, but on an absolutely insane cosmic scale. First, gravity grabs onto some nearby gas. But it doesn't just fall straight in. Oh no, it forms this chaotic, spinning platter of doom called an accretion disk. And as all that material grinds against itself, the friction and pressure gets so intense that it heats up to millions of degrees. And that's when the whole thing just blazes with energy, shining brighter than all the stars in the galaxy combined. Okay, but not just any light will do. To see it process this hot and this violent, you need a very specific tool. You basically need the ultimate X-ray vision. This is the absolute critical wavelength for studying black holes. Here's why that's so important. If you look at a galaxy in visible light, like you see on the left, you're seeing its beautiful skin, all the pretty stars and cool clouds of gas. But X-rays, on the right, they're like a cosmic CAT scan. They just slice right through all that dust and gas and show us the raw, high-energy violence happening right at the core, literally on the doorstep of the event horizon. So this is a huge deal. X-rays give us a direct line of sight to the inner sanctum. This is where we can actually watch black holes grow in real time. And it's also the launch pad for these enormous jets of energy that can literally reshape their entire host galaxy. It's a scientific 2-for-1. Okay, so how do we actually use these X-rays? Well, astronomers have found there are basically two ways that black holes feed. First up is what you could call the standard cosmic diet. This is what we see when we observe something called an active galactic nucleus, or AGN for short. So what's an AGN? Basically, it's a supermassive black hole that's just constantly eating. It's not a crazy feast, more like a steady, persistent meal. And this constant feeding makes the center of the galaxy shine with an unbelievable brightness, especially in X-rays. And by studying that steady X-ray light, oh man, the amount of information we can pull out is incredible. We can figure out the black hole's mass. We can even measure its spin, how fast it's rotating on its axis. We can map out the shape of the gas swirling in. And we can see exactly how those powerful galaxy-shaping jets get launched. It is an absolute goldmine of data. And it gets even better, because even in a steady AGN, that X-ray light isn't perfectly flat. It flickers. And these super fast flickers, happening over just minutes to hours, well, that's incredible. It means we're tracing activity happening right at the point of no return, which lets us test the very limits of Einstein's theories.
But of course, the universe isn't always so calm and steady. Sometimes that standard diet gives way to an all-out binge. And this is when we get to study these incredible, extreme, transient events.
Yeah, forget the steady meal. This is the cosmic equivalent of a food fight. These events are sudden, they are messy, and the power they unleash is it's almost impossible to comprehend. These are some of the most violent things we know of in the entire universe. So, first on the menu, we have what's called a tidal disruption event, or a TDE. This is what happens when a star makes a very, very bad decision and wanders just a little too close to a supermassive black hole. The gravity on the near side of the star is so much stronger than on the far side that the star gets pulled apart like spaghetti. It's spectacular and, frankly, terrifying. So why is this cosmic catastrophe so important for science? Because with X-rays, we get a front row seat to the whole show. We can literally watch, in real time, as the shredded guts of that star form a brand new accretion disk from scratch. It's like watching a black hole's feeding frenzy begin.
Next up is something a lot weirder. It's called a quasi-periodic eruption, or QPE. And what it is this mysterious, rhythmic bursting of X-rays from a galaxy's core. It's almost like we've detected some kind of cosmic heartbeat, but honestly, we're still scrambling to figure out what's causing it. Now, one of the most exciting theories out there is that these QPEs are caused by a smaller object, maybe a stellar mass black hole that's orbiting the big one. And if that's true, well, that kind of system should also be pumping out gravitational waves, giving us a whole new way to see the universe. It's a real game changer.
So where does all of this leave us? Well, all this amazing research is pushing us right to the edge of a new era. We're about to turn the page to the next cosmic chapter, and it's all going to be driven by the future of X-ray astronomy. You see, to get the full story, we need both sides of the coin. We have to study the slow and steady standard diet of the AGN, and we need to catch the dramatic, messy binges of these transient events. Put them together, and we finally start to get a complete picture of how these cosmic giants grow and evolve over billions of years.
And that's why right now is such an unbelievable time for this field. The next generation of X-ray telescopes, new surveys that scan the sky for anything that changes, and our incredible new ability to detect things like gravitational waves, all of it is poised to completely revolutionize everything we thought we knew about black holes.
It just leaves you wondering, doesn't it? We've used X-rays to peel back this one amazing layer of mystery around black holes. But what other incredible secrets are still out there, hiding in plain sight, just waiting for us to look at the universe with X-ray eyes?